Hi everyone. In the previous video lecture, we have discussed about the ionic or electrovalent bond. What is an electrovalent or ionic bond? How this ionic bond is formed? What are the conditions required for the formation of an ionic bond? What are the important characteristics or the general characteristics of an ionic bond that we have discussed in detail along with their examples? And why do chemical bond formation takes place, that also we have discussed. So one of the most important criteria for the formation of ionic bond was the lattice energy. There we have just mentioned for the formation of any ionic compound, the lattice energy or the energy released during the formation of 1 mole of an ionic compound from the required number of cations and anions should be large negative. So the energy criteria says the lattice energy of the ionic compound formed should be large negative. So now we are going to take up what is lattice energy, how this can be visualized in graphical form, and how we can calculate the lattice energy and the comparison of lattice energies of various ionic compounds. So coming to this term lattice energy, so first of all we have to define what is lattice energy. Now lattice energy is defined in two different ways. First, it is defined as the energy released during the formation of 1 mole of an ionic compound from a required number of cations and anions. So we may have more than one cation or we may have more than one anion. Now from this required number of cations and anions, we should be able to get only 1 mole of the ionic compound. So during this formation of 1 mole ionic compound from required number of cations and anions, some energy is released, and that energy released is defined as the lattice energy of the compound. Now this is defined in terms of energy released during the formation of the ionic compound. On the other hand, the lattice energy can also be defined as, suppose we have an ionic compound, 1 mole of an ionic compound. Now to break this 1 mole of ionic compound, to dissociate this 1 mole of an ionic compound, how much energy is to be supplied? That energy required to break or to dissociate 1 mole of an ionic compound into its constituent cations and anions. So this energy required to break 1 mole of ionic compound into constituent cations and anions is also defined as the energy in terms of lattice energy. So in both the definition, the way of defining lattice energy is different, but the numerical value of this energy will always be same. In the first way, in the first definition, the energy released, so that value will be negative. In the second definition, that is energy required or the energy consumed, then lattice energy will be positive. So for the same substance, energy released in terms of lattice energy in terms of energy released or lattice energy in terms of energy required to break will have same numerical value, but sign will be opposite. So this is how we define the lattice energy. So once we define this lattice energy, now let's visualize this lattice energy in terms of graphs. So suppose we have this M plus combines with X minus, so we have cation, we have anion, and this gives you Mx ionic solid. So this is formation of 1 mole of ionic compound. So here this energy is defined as minus A, some kilojoule per mole. So this is lattice energy, that is defined in terms of energy released during formation of 1 mole of ionic compound. On the other hand, we take this same compound, that is Mx, 1 mole of ionic compound. Now we have to dissociate this 1 mole of ionic compound into the constituent cations and the anions. Now since we are breaking the bond, so energy must be consumed. In this case, the lattice energy is defined as plus A. So in both the case, look at this, the absolute value of lattice energy for the same substance in two different ways will be having same numerical value, but sign will be opposite. So this is the way how we can define the lattice energy. So while using this lattice energy, we have to be very specific whether this is defined in terms of energy released or in terms of energy required. Now coming to this graphical representation of this lattice energy. This is 0, this is positive value, this is negative value. Now this is the potential energy of the system. Now let's take this cation and anion, Mx plus and X minus. When they are at very large distance, there is no attractive force or no repulsive force. दोनों के बीच में कोई attractive force और कोई repulsive force है नहीं. अब ये धीरे 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 आमने सामने रखेंगे. When they are brought closer to each other, they are having opposite charge. So since they are having opposite charge, as they come closer to each other, the attractive force between these two ions will increase. As the attractive force increases, the potential energy of the system will decrease. So as the distance between the ions decreases, the attractive force, that is what we call as the Coulombic force of attraction, will increase. As the attractive force increases, the potential energy of the system will decrease. So look at this. This is the distance, let this be R, distance from between the ions. So at very large distance, the potential energy is approximately 0. So as the distance decreases, the attractive force increases. As the attractive force increases, the potential energy of the system decreases continuously. So this is the attractive force. This represents attractive force. Now on the other hand, these two ions also has a nucleus, also has an electron. Now look at this. The electrons of M plus and X minus both are having same charge. So same charges undergoes repulsion. So when they are at very large distance, the electrons of X minus and the electrons of M plus N will have zero force of repulsion or attraction. As the distance between these two decreases, the repulsion between the electrons of X minus and that of M plus ion will increase. As the repulsive force increases, the potential energy of the system will also increase. Now take the other way around. Both these ions also has a nucleus, and nucleus of both will be having same charges. So as the distance decreases, the repulsive force between the nucleus also increases. So as the distance between the two ions decreases, the repulsive force between the electrons and that between the nucleus also increase continuously. So we represent this repulsive force so this represents a repulsive force between the nuclei as well as between the electrons of the two ions. So we are having two contrasting factors here. As the distance decreases, both the attractive force as well as the repulsive force increases continuously. But now at a certain distance there has to be formation of bond. So for this formation of bond, the requirement is the attractive force should be having a dominating effect over the repulsive force. So now we have to combine these two. Now combining these two, that is attractive force as well as repulsive force, when we combine these two, the net variation of potential energy comes like this. This is the net resultant variation of the potential energy by combining this attractive force as well as the repulsive force. Now if you look at this, why this is happening? Now comparing between this repulsive force and attractive force, the attractive force dominates over the repulsive force. So as the distance decreases, since the attractive force dominates over the repulsive force, so energy continuously decreases, and at this particular point the energy reaches the minimum value. So this particular point where the potential energy reaches the minimum value, that distance, this distance that is defined as R0, that is the equilibrium distance. So at this equilibrium distance, the potential energy of the system, that is this mx and is minimum. So that minimum point corresponds to the formation of bond between M and X. So at this particular point, that is R0, the formation of an ionic bond takes place. That is, the attractive force between the two ions is having the maximum value at this particular point. Since the bond formation takes place, so energy corresponding to this particular point is defined as the lattice energy. So potential energy is minimum and this corresponds to the lattice energy. Now after this point, as the distance decreases, there is steep increase in the potential energy. That means beyond this point, the repulsive factor dominates over the attractive force. So this portion of the graph, attractive force dominates over repulsive force. Beyond this point, the repulsive force dominates over the attractive force. So this particular distance, that is the equilibrium distance, at which bond formation takes place. That is R naught. So this is how we visualize the variation in energy as the distance between these two ions varies. So what I am to saying is, as the distance decreases, both repulsive force and the attractive force increases, but initially the attractive force dominates over the repulsive force, or the magnitude of attractive force being greater than that of repulsive force, the potential energy continuously decreases, reaches a minimum point. So at this minimum point, that is R naught, which is known as equilibrium distance, the bond formation takes place and the potential energy becomes minimum, and this minimum potential energy corresponds to the lattice energy of that particular compound. Beyond this point, distance slightly decreases, energy steeply increases. That means beyond this point, this portion of the graph, repulsive factor is having much larger than that of the attractive force. So this is how we define lattice energy graphically. Now the question is, we have to calculate this lattice energy. Now let's calculate this lattice energy. Calculation of lattice energy. Calculation of lattice energy. Now this lattice energy, we have two different methods to calculate lattice energy. One is known as theoretical method, the other one is known as experimental method. Now coming to the theoretical method, for calculation of lattice energy. Now we define this lattice energy in some of the books. This is defined as U. So I'll make this U as a lattice energy. So theoretical calculation of lattice energy is based on an equation known as Bond-Lambda equation. So we have to use this equation to define the lattice energy. So based on this Bond-Lambda equation, lattice energy U is defined as minus NA, that is Avogadro number. A is a constant that I am going to define later on. E square Z plus into Z minus divided by R naught 1 minus 1 by N. So this is the equation which is known as Bond-Lambda equation. These are the two scientists who define this equation based on theoretical consideration. U is the lattice energy, Na is Avogadro number. Why we are using Avogadro number? Because this lattice energy is always defined for 1 mole of the ionic compound formation. So we have 1 mole. A is known as Medulum constant. So this is a constant which is specific for a specific crystal. So this A depends on the crystalline structure. We are not going to deal this in detail, because each ionic compound has some regular arrangement of the ions in space, which gives rise to crystalline structure. So that crystalline structure, how the ions are arranged, the coordination number, distance between the ion, all this is being taken care by this constant known as Medulum constant. So for each and every crystal, we have different values of this A. E is the electronic charge on electron, that is 1.6 into 10 power minus 19 coulomb. Z plus E, charge on cation plus for cation. Z minus, charge on anion. R naught, This is the distance between cation and anion, this distance, equilibrium distance. This equilibrium distance R naught, and is known as bond exponent. Again, this bond exponent depends on the types of lattice. So for every ionic compound we have different values of N, we have different values of Z plus, ZE, R naught, except this Avogadro number and E, both are having same value for different types of crystals or ions. Now if you look at this equation very carefully, this lattice energy depends on two factors, mainly two factors. Look at this, this depends on, is proportional to 1 by R naught. That means if the distance between the ions at which the bond is formed, if the distance is more, lattice energy will be having larger value. So if distance is more, you will be less. If the distance is less, you will be more. So lattice energy is inversely related to the distance between the ions. So for this lattice energy to be large, the distance or the size of the ion should be small. To smaller size ions will have larger lattice energy. This negative represents energy released. And the second factor is this lattice energy is directly proportional to the product of charge on the cation and anion. So greater is the charge on the cation and anion, larger will be the lattice energy. If the charges on cation and anion is less, then the lattice energy will be less. Now let's explain by use of this example. Take this example. We have this lithium fluoride, calcium fluoride, and take this magnesium sulfide. Let's have a comparison. If you look at this, this is lithium plus, fluorine minus, calcium 2 plus, fluorine minus, magnesium 2 plus, sulfide 2 minus. Now look at this, Z plus is equals to Z minus equals to 1, Z plus equals to 2, Z minus equals to 1, Z plus equals to 2, and Z minus equals to 2. So therefore Z1, Z plus Z1, Z plus Z minus, so this is 1, this is 2, this is 4. So is the value of Z plus Z minus. So look at this, Z plus Z minus, that is 1, this is 2, this is 4. So the product of charges on the cation and anion increases, so the lattice energy will increase in this way. Take this, we have this lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Now look at this, Z plus equals to 1, Z minus equals to 1. So the product of charges is always equals to 1 for all these ionic compounds. R plus is a constant because in all these cases we have Li plus. So R minus increases from fluoride to chloride to bromide, bromide to iodide. So if the R minus increases, so this R naught, which is R plus plus R minus, increases from fluoride to chloride to bromide to iodide. So as the distance between the ions increases, lattice energy decreases because lattice energy is inversely related to the size. So therefore lattice energy decreases in this way. So this is how we compare the lattice energy based on this bond length equation. So we have to keep in mind lattice energy is inversely related to the distance between the ions, and this is directly proportional to the charge product of the charges on the cation and anion. So this is about theoretical calculation of lattice energy. Now coming to experimental determination of lattice energy. Experimental method. Now this experimental method for determination of lattice energy is by use of a cycle known as Born-Haber cycle. So we are going to develop a cycle, and this cycle is known as Born-Haber cycle. These are the two scientists who get this cycle for exact or the experimental determination of the lattice energy, because all the tasks that we are going to use it can be defined experimentally defined quantities. So we have this Born-Haber cycle. Now this Born-Haber cycle is based on Hess's law of constant heat summation, or simply known as Hess's law. So while developing this Born-Haber cycle use a law which is known as Hess's law. So method for determination is known as Born-Haber cycle, but Born-Haber cycle is based on a law which is known as Hess's law of constant heat summation, or simply Hess's law. Now let's explain this by use of this example, that is formation of NaCl. So we can explain this experimental method by use of this formation of NaCl, sodium chloride. Now let's take this. We have looked at this sodium solid combines with this chlorine gas, half of this chlorine gas, and this gives you sodium chloride solid. So simply we say sodium chloride formation is, we have sodium solid combining with half moles of chlorine gas to give you 1 mole of sodium chloride. Now this is the formation of sodium chloride from their elements, sodium and chlorine. Now this formation of sodium chloride, there is a formation of a compound. So during the formation of a compound, always energy is released, and let's suppose this energy that is defined as delta HF, that is enthalpy of formation. Enthalpy of formation, because we use this term enthalpy to define energy. So enthalpy of formation of sodium chloride, energy released during the formation of 1 mole of sodium chloride from constituent elements. This is not equals to lattice energy. Lattice energy was defined from ions. This is not the ions, but this is elemental sodium and elemental chlorine. So use of this elemental sodium and elemental chlorine to form sodium chloride, energy is released, which is known as enthalpy of formation, delta HF. Now during the formation of ionic compound, there must be formation of ions, that is cations, and anions should be formed. So look at this. We convert this sodium into sodium gas, because to define ionization energy we need to have a neutral isolated gaseous atom. So this is conversion of sodium solid to sodium gas. So conversion from solid to gas, obviously we have to supply energy, and this energy is defined as enthalpy of atomization, because we are converted into atom. So this is always positive, means you have to supply energy, or we can say enthalpy of sublimation, sodium solid to sodium gas. Now we have this sodium gas. Now this sodium gas is to be converted into sodium ion means we have to release electron, so that this is converted into cation, and still this is in gases. Now again look at this removal of electron, that is ionization process, and we have a term which is known as ionization energy. So during this process we have to supply energy in the form of enthalpy of ionization. So this is again the positive. So ultimately we have to convert this sodium solid into sodium ion. So this involves two steps. First is atomization step, for which we have to supply energy. Second, from this gaseous metal we have to remove electrons, so that this is converted into the cation. Again we have to supply energy. Now on the other hand, this chlorine gas, already this is in gas, but we have molecular form. We have chlorine-chlorine bond. Now we have to break this bond. That is, this is to be converted into chlorine atomic form. This was molecular form. Now this is to be converted into atomic form. Now we have to supply energy in the form of dissociation energy. Dissociation of molecular chlorine into atomic chlorine. Now since we are using half, so this must be multiplied by half. This enthalpy is defined for 1 mole, but since we are having half mole, so we have to multiply this by half. Now since we have this chlorine gas, now this being a non-metal, this is to be converted into chloride ion, again in gaseous state. So the electron released by sodium ion will be taken up by this chlorine, and is converted into chloride ion. So during this there is an energy change which is known as electron gain enthalpy, and the electron gain enthalpy values for halogens is always negative. So we have this negative. Now so we have sodium ion, we have chloride ion. So when they are placed side by side, these two combines to give you this 1 mole of ionic compound, that is NaCl. Now this process, formation of 1 mole of NaCl from sodium ion and Cl minus, and again energy is released, and that energy released, that is what we call as the lattice enthalpy. So this is defined in terms of energy release, so this must be negative. So all these terms involves energy, and this energy can be experimentally derived. So this is what we call as experimental methods. This total cycle, so we have a cycle here. So this cycle is known as Born-Haber cycle. So according to this Hess law, for the same process, so this is formation of NaCl, that is direct process, single step. This is multiple step. So for the same process, if the process is taken in a single step or the multiple step, the energy change will always be the constant. So according to Hess law, energy change for the single step, this delta HF, that is energy change during this single step, is equals to energy change during this multiple steps. So energy change, that is delta HF, that is enthalpy of atomization, plus delta H ionization energy, plus half of dissociation energy, plus electron gain enthalpy or electron affinity, plus lattice energy. So if lattice energy is to be defined, then we should be having this value. So from this we can easily define lattice energy. So this is what we call as Hess law. So energy of single step and energy of multiple step, both are exactly same. So by use of this we can define exact lattice energy of an ionic compound, because all these terms involved here. This is experimentally derived quantity. And the other equation that is known as Bond-Lambda equation, that is just based on the theoretical prediction. So by use of this, we can just compare their values based on the distance or based on the product of the charges. So this is all about lattice energy. What is lattice energy? What is the significance of lattice energy? How chemical bond formation takes place, and the two different methods for determination of lattice energy. By use of this, we can easily compare the lattice energy of different types of ionic compounds. By use of this, both this theoretical value as well as the experimental value. Now, having learned this lattice energy and the basics or the concept of ionic or electrovalent bond, now we are going to take up a case when these ionic character possess some covalent nature also. That means every ionic bond is not 100% ionic. Along with this ionic, we also have some covalent nature. The only thing we are mentioning is, if the ionic character is more, then we say this is ionic compound. If the covalent character is more, then we say this is covalent in nature. But every ionic compound or every bond in which we have ionic bond or the electrovalent bond do possess some covalent character. So we have to define the covalent character in an ionic compound. Covalent character in ionic compounds or ionic bond. Now this covalent character in ionic bond is explained by a rule which is known as Fajan's rule. So we are going to take up what is Fajan's rule, and by use of this Fajan's rule we can compare the covalent character in an ionic compound. So these Fajan's rule, we are discussing what is the Fajan's rules, and by use of this Fajan's rule we are going to compare the covalent character in different ionic compounds. Now this Fajan's rule basically consists of two components. One is known as polarizing power simply I am mentioning this is P. The other one is known as polarizability, simply said PZ. We have polarizing power, we have polarizability. Polarizing power, this is defined only for cation. So cations are measured in terms of their polarizing power, and this polarizability is only for anions. So anions are measured in terms of their polarizability. So the covalent character in an ionic compound covalent character in ionic compounds is directly proportional to the polarizing power of cation, is also directly proportional to the polarizability of the anion. So greater is the polarizability of anion, more will be the covalent character. Greater is the polarizing power of the cation, more will be the covalent character. So therefore, covalent character is directly proportional to the product of polarizing power and the polarizability of anion. So we can compare the polarizing power and the polarizability of the cation and the anion. So coming to the first term, that is polarizing power. polarizing power of cation. Now this polarizing power of cation is the tendency of the cation to disturb or to deform or to distort the electronic field of anion. The tendency of the cation to disturb, to distort, to deform the electronic cloud of the anion is defined as the polarizing power. So what we are saying is, when we discuss about covalent nature, there must be tendency for overlapping of orbitals. In case of ionic compound, ionic bond, there is no overlapping of atomic orbitals. Whereas if the tendency for the overlapping of atomic orbital increases, then the covalent character will increase. So covalent character is defined in terms of tendency for these atomic orbitals to overlap. So what I am saying is, the polarizing power is the ability or the tendency of the cation to disturb or to distort or to deform the electronic cloud of the anion. If this cation can disturb the electronic cloud, means this cation will affect the electronic field. If this withdraws or disturbs the electronic field of the anion, that means there is some chances for overlapping of atomic orbital. That is what we call as the polarizing power. So this is defined as tendency or the ability of cation to disturb or distort or deform the electronic field of anion. This is what we call as the polarizing power of the cation. So more is the polarizing power of the cation, the more it will disturb the electronic field of the anion, the more it will have a tendency to overlap with the atomic orbitals. So more is the tendency for this overlapping of atomic orbital, more will be the covalent character. So we have this polarizing power. So now the question is, factors on which this polarizing power depends. Factors on which this polarizing power depends. So the first factor is the charge. Charge on the cation. Now, as the charge on the cation increases, the effective nuclear charge increases. As the effective nuclear charge increases, this cation will have a stronger effect on the anionic electron field. So as the effective nuclear charge is more, this cation will have more tendency to disturb or distort the electronic field of anion, because as a charge density, positive charge density on the cation is more, so this will have more polarizing power. So the polarizing power is directly proportional to the charge on cation. So take this, we have this iron plus 2 and iron plus 3. So look at this, we have plus 2 charge, we have plus 3 charge. So as the charge increases, the polarizing power increases. So as the polarizing power increases, the covalent character will also increase. So the compounds formed by iron plus 3 will be more covalent. Compounds formed by iron plus 2 oxidation instead will be more ionic or less covalent. Similar, look at this. We have, look at this, lithium plus sodium plus potassium plus rubidium plus cesium plus. Now look at this, moving from lithium to sodium. Oh, sorry. There is copper plus copper plus 2. So copper plus 2 being having more charge density, so we'll be having more polarizing power than copper plus 1. So in case we have different cations, for these different cations based on the charge we can easily compare the polarizing power. So as the charge increases, effective nuclear charge increases. As the effective nuclear charge increases, the polarizing power of the cation will also increase. This is first factor. Second factor is the size of cation. The polarizing power of cation is inversely related to the size of cation. As the size increases, the polarizing power of the cation will decrease. That means larger size cation will have less polarizing power than smaller size cations. So the compounds formed by larger size ions will be more ionic, and the compounds formed by smaller size cations will be more covalent. So based on this size, look at this, we have this lithium plus, sodium plus, potassium plus, rubidium plus, cesium plus. So moving down the group, size of this cation increases. As the size increases, polarizing power decreases. As the polarizing power decreases, covalent character decreases or the ionic character will increase. So size increases. As the size increases, the polarizing power will decrease. So the compounds formed by lithium will be more covalent, and the compounds formed by cesium will be more ionic. So this is based on the size of cation. So polarizing power is inversely related to the size of cation. Then the third factor is electronic configuration. Electronic configuration of the cation. Now this electronic configuration we can divide into two headings. One is known as inert gas configuration, the other one is known as pseudo inert gas configuration. Inert gas or the noble gas configuration means having 8 or octet in valency cell, having 8 electrons in the valency cell, that is known as octet 8 electrons. In case of pseudo inert gas configuration, we have 18 electrons. So 18 electron means we have 10 electrons in D and 2 electrons in S and 6 electrons in P. So the valency shell should have 18 electrons. So this electronic configuration having these types of form are known as pseudo inert gas configuration. Now look at this. This D electron, the shielding power of or the screening constant or the screening effect of D orbital electron is very poor compared to that of S and P. So these inertial orbital 10D electrons cannot shield these S or P electrons. As a result, there is a contraction in size. Due to this contraction in size, the polarizing power of those metal ions having pseudo inert gas configuration will be having more polarizing power. So poor shielding effect. So electronic configurations of metal having pseudo inert gas form will be having more polarizing power. So this is the polarizing power of the cation. Take this sodium plus and copper plus. If you look at this, sodium plus chargation, sodium is having 8 electrons in the valence shell, copper is having 18 electrons in the valence shell. So we have a pseudo inert gas configuration. If you look at it, the size of these are approximately same. So these having the pseudo inert gas configuration, the polarizing power of copper plus ion will be more. So the compounds formed by copper plus ion will be more covalent than sodium ion. Similarly, we can take this K plus and silver plus. Again, look at this. Potassium is having 8 electrons, silver is having 18 electrons, so we are having a pseudo inert gas configuration. Again, we have a poor shielding effect of 10 d electron. So the polarizing power of silver plus ion is greater than that of potassium ion. So along with this, we have to see the electronic configuration if we have this pseudo inert gas configuration or not, along with this charge and this size. So this is the polarizing power of the cation. Now coming to polarizability of anion. Polarizability of anion, that is PZ. Now cation is disturbing or deforming or destroying the electronic field of anion, that is defined as the polarizing power of the cation. Now this anion is letting its electronic field to be disturbed by the cations. So how much this anion is giving its electronic field to be disturbed by the cation, that is known as the polarizability of the anion. So the polarizability of anion is the ease with which the electronic field of this anion can be disturbed by the cation, that is known as the polarizability. The ease with which the anion is allowing its electronic field to be disturbed by cation. This is known as the polarizability of the anion. So we have the polarizability of anion. Now look at this. What are the factors on which the polarizability of anion depends? So coming to the factors affecting the polarizability of anion, first factor as well as we have is charge. Now as a negative charge on the anion increases, the size of anions increases. As this negative charge increases, the repulsive factor increases. As the repulsive factor increases, means distance from the nucleus increases, the electronic field can easily be disturbed by anion. So this polarizability is directly proportional to the charge. So as the negative charge increases, the polarizability also increases. So we have to see the charge on the anion also. As the negative charge increases, the polarizability also increases. As the polarizability increases, the covalent character will also increase. Then next is size of anion. Now as the size of anion increases, the distance between the nucleus and the valence shell increases. as the distance between the valence shell and nucleus increases, the attractive force decreases. As the attractive force decreases, the ease with which this electronic field of the valence shell can be disturbed increases. So based on this, we can say the polarizability of anion is also directly proportional to the size of the anion. So look at this. We have this fluoride, chloride, bromide, iodide. Now charge remains same, but the size increases from fluoride to chloride to bromide to iodide, because down the group size increases. So as the size increases, the polarizability of the ions also increases. So the I minus has got the strongest or largest polarizability, F minus has got the least polarizability. So the more is the polarizability of anion, more will be the covalent character. So the compounds of iodide will be more covalent, and compounds of fluoride will be more ionic or less covalent. So this is the polarizability of anion. And now combining these two, we are saying covalent character is directly proportional to the polarizability of anion as well as the polarizing power of cation. So more is the polarizing power and polarizability of anion, more will be the covalent character. So let me take this example. Take this lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, cesium fluoride. So if you look at this polarizability, that is F minus. So in all this case we have Ln plus minus plus minus plus minus plus minus plus minus. So F minus, in all this case anion is fixed F minus, to charges be same, size is also same. So charge on anion is -1, charge on size of anion is also fixed. So the polarizability of anion is constant. But what about, look at this, polarizing power. So we have, look at this, lithium plus, sodium plus, potassium plus, rubidium plus and cesium. Now down the group size increases. So the polarizing power of cation is inversely related to the size. So as the size increases, the polarizing power decreases. So as the polarizing power decreases from lithium to cesium, the compound formed by lithium will be the most covalent and the compound formed by cesium will be the least covalent or the most ionic. So the covalent character, covalent character, lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride. So this is the most covalent, this is most ionic. I hope you got this point. So we are discussing polarizing power and the polarizability. Take the second example. Lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Now we have the same cation and different anion. So in this case, polarizing power of cation, that is lithium plus ion, that is the constant. So we are having same charge and same size of the cation. So the polarizing power of cation is fixed. Now coming to polarizability. Now we have different ions, fluoride, chloride, bromide, iodide. So moving down the group, size increases. As the size increases, the polarizability of anion also increases. So we have fluoride, chloride, bromide, iodide. So polarizability of anion increases in this way. So therefore, the covalent character, lithium fluoride to chloride, chloride to bromide, bromide to iodide. So this is most ionic, this is most covalent. Take this. Sodium fluoride, calcium fluoride. Let's take this case. So we have look at this polarizability, that is F minus. We are having a constant here. This is Na plus F minus, calcium plus 2 F minus. We have this polarizing power. So look at this Na plus Ca plus 2. Now we have different cations, sodium ion and calcium ion, or we can say take this magnesium. Take this magnesium. So sodium ion charges is plus 1 plus 2. Both are isoelectronic, having same number of electrons. But if you look at this, moving from sodium to magnesium, size decreases. So as the size decreases, polarizing power of cations increases. Similarly, moving from sodium to magnesium, charges also increases. So as the charge increases, polarizing power of the cation also increases. So polarizing power is directly proportional to charge. So charge increases, polarizing power increases. Size decreases, polarizing power also decreases. So therefore the polarizing power of magnesium is greater than that of sodium. So therefore this magnesium fluoride will be more covalent than sodium fluoride. So compounds formed by magnesium will be more covalent than compounds formed by sodium. Take this, we have calcium oxide, and suppose this is calcium sulfide. Here we can test magnesium oxide and magnesium sulfide also. Take this magnesium oxide and magnesium sulfide. So magnesium plus 2, oxide minus 2, magnesium plus 2, sulfide minus 2. Now if you look at this polarizing power, that is magnesium plus 2, that is constant. In both the cases we are having magnesium plus 2. Size also same, charges also same, cation is fixed. So we have magnesium ion, that is polarizing power is fixed. Now coming to polarizability, we have oxide ion, we have sulfide ion. Now if you look at this, charges on this anion is same, so we cannot differentiate the polarizability of the anion with respect to the charge, because we have plus 2 plus 2. But we can have the difference in size. So moving from oxygen to sulfur down the group, oxygen, sulfur, selenium, tellurium, down the group size increases. So as the size increases, the polarizability of anion also increases. So therefore the polarizability of sulfide ion is more than that of anion due to larger size. So since the polarizability of sulfide ion is more than that of oxide ion, the covalent character of this magnesium sulfide is greater than the covalent character of magnesium oxide. So by use of this we can compare. Okay. So this is more ionic, this is more covalent. Take this calcium oxide and magnesium oxide. Look at it, this is plus 2, minus 2, plus 2, minus 2. So polarizability, there is O2 minus, we have this fixed. Then we have to see the polarizing power of cation. So we have calcium ion and magnesium ion. Now the charges on cation is same, plus 2 plus 2, but we can have difference in size. The size of calcium ion is greater than the size of magnesium. So smaller size, larger size. As the size of magnesium is smaller than that of calcium, this magnesium will have more polarizing power than that of calcium. smaller size. So therefore the compounds formed by magnesium will be more covalent than compounds formed by calcium. So if you look at it, this is covalent character. Magnesium oxide is more covalent than calcium oxide. So by use of this polarizing power and polarizability that is based on Fajan, so we can easily compare the covalent character in any ionic compound. Now as the covalent character increases, the general features of ionic compound will so decrease in value. So by use of this Fajan rule, we can easily predict the covalent character in ionic compounds. So this is how we visualize this ionic bond. So every ionic bond is not 100% ionic, but along with this ionic character we also have some covalent character. So take one more example. Take this sodium iodide and cuprous iodide. Sodium plus copper plus, I minus, I minus. If you look at this, the polarizability that is of I minus is constant, but we can see the polarizing power. So we have Na plus and copper plus. Now look at this. This sodium ion, if you look at this size is approximately same for the sodium and copper, but this has got 8 electrons, but this has got pseudo inert gas configuration. So we have discussed a case, if the cation has got pseudo inert gas configuration, then due to the poor shielding effect of d orbital electrons, the polarizing power of cation increases. So the polarizing power of cation is more than that of copper is greater than that of sodium, that is pseudo inert gas configuration. Therefore copper iodide is more covalent, sodium iodide is more ionic. Similarly, we can take this potassium iodide and silver iodide, K plus I minus, Ag plus I minus. So the polarizability of I minus is again fixed or constant, but the polarizing power depends on this. So this has got 8 electrons, but this has got pseudo inert gas configuration. So therefore the polarizing power of Ag plus I is greater than that of K plus, and so the compounds formed by Ag plus N will be more covalent than compounds formed by K plus N. So this is the covalent characters. So this takes into account all the factors that we have discussed, by use of which we can easily compare the polarizing power and the polarizability of the anion. So this is all about covalent character in ionic compound. We have used Fajan's rule. We have defined two terms, polarizability, polarizing power. We have defined them, and we have also discussed the factors on which this polarizing power and polarizability also depends. So thank you.